Okay, here is the second part of this section. Now in this part, what we do is we are going to evaluate the surface integral of a vector field. Now let me draw a picture to explain this concept. So we have this xy plane, xy and z axis, and in 3D we have a surface S. So we have a surface S. This is our surface S. Now on this surface we have a vector field. So at every point we have a vector. So maybe this vector field points in different directions at every point, different magnitudes. So we have a vector field F. Let's say this is a vector field with the components P, Q, R. Usually these are functions of x, y, and z. Let's have a vector field F. Now let's define the surface integral of a vector field. If you recall the line integral of a vector field, so what we did was we considered the tangential component of the vector field along the line or along the path. But now when we consider the surface integral of a vector field, instead of taking the tangential component, we take the normal component to the surface S. Okay. So let's define this. So we have a vector field F with the components if P, Q, R. Let's write it like this. Three components. This is a vector field in R3. It's a vector field in space, and say S, and S is the surface with the equation C equals to little f of x comma y, that is defined on D, that is defined on the domain D. So that's your surface S. This is your surface S. The domain of this surface is on the xy plane, and that's your domain D. Let me choose a color like this. That's your domain D. So in other words, if you project the surface S onto the xy plane, you should see your domain D. That's your domain D. Okay. So now we are ready to define the surface integral. So then the surface integral of the vector field F over the surface S is defined like this. So we have a double integral of F dot ds over the surface S. And note that I drew an arrow on top of this s to denote this is a vector quantity. This equals to double integral of f dot n ds the surface S. This equals to double integral of the vector field F, which is given by PQR dot minus F sub x minus F sub y and 1 dA over the domain D. I will explain this part after 1 or 2 minutes, but this is the way we define the surface integral of a vector field. And this is f dot with the normal unit normal vector of the surface S, and the unit normal vector of the surface S is given by this, and instead of this ds we have dA, and this double integral is over the domain D. And this is what really happened. So so this is a side note. Okay, now if you have a surface with the equation C equals to f of x comma y, the unit normal vector is given by the gradient of C minus f of x comma y over its magnitude. Actually, we learned this one in chapter 11. Now this gradient vector equals to minus f sub x minus f sub y and 1. Its magnitude is square root of 1 plus f sub x squared plus f sub y squared. So basically this is your unit normal n. Now if you recall the formula for ds, you will get ds equals to square root of 1 plus f sub x squared plus f sub y squared dA over the domain D. Now dA is an area element on the domain D. So now if you consider the double integral of S of f dot n ds, this equals to, what is your f? F is PQR, it has 3 components, and n equals to minus f sub x minus f sub y 1 over square root of 1 plus f sub x squared plus f sub y squared. Now instead of ds I can write square root of 1 plus f sub x squared plus f sub y squared dA as you can see. Now we can cancel this term with this, and this becomes, now we have the dot product of two vectors in R3 which equals to a scalar that equals to minus p times f sub x minus q times, q is the second component of the vector field, times f sub y plus r dA over the domain D. Okay, now this is the derivation of the surface integral formula. Okay, now so this is a vector surface area element. This ds equals to n ds. Now note that this is a vector surface area element which equals to n times the scalar surface area element ds.